Okay, welcome back. So today we're going to continue talking about the chain rule. So yesterday we talked about case one, where say maybe we have a function that depends on two variables like x and y, but both x and y are functions of only one variable. Maybe we called that t. So today we're going to talk about case two. So now maybe we have some z that's equal to a function of x and y. But x and y are functions of two variables. So we say that x is equal to a function g that relies on s and t, and y relies on a function h, which is also a function of s and t. So the question is, what are partial z, partial s, and partial z, partial t? Since z is now indirectly a function of s and t. Right? Because if x and y are functions of s and t, then z is inherently a function of s and t, and we can talk about their partial derivatives. So we can take partial z, partial s, and partial z, partial t. So when we did partial derivatives, the other variables were fixed, right? They were these constants. So we can kind of use the same logic that we did from case one, where we look at these differential forms. And we can get to the point where it's almost remarkably the same thing, or if we have partial z, partial s, this is partial z, partial x, partial x, partial s, plus partial z, partial y, partial y, partial s. And then we also have partial z, partial t is equal to partial z, partial x, partial x, partial t, plus partial z, partial y, partial y, partial t. So very similar to the chain rule for case one, but now we have two things that we can do. We can take a partial with respect to s and a partial with respect to t. And notice here that the second term in each of these groupings is no longer total derivative, but this partial derivative. Right? And the same kind of formulation as before. We have the first term has partial z's on the top, followed by all of the coordinates that f is directly related to, so x, y. And then the second terms are the diagonals match again. So we have partial x's here and partial y's here, followed by the denominator here being the partial that we're taking respect to. So you can imagine that we can extend this into higher dimensions very similar to how we did with the case one. So if maybe z is a function of x, y, and z is, well, I guess maybe we shouldn't do z. Maybe we can say, it's another function of a. has a there. And a is also a function of s and t. You can just add another term here that corresponds. Okay. So here we call s and t are the independent variables. X and Y are the intermediate variables. And Z is the dependent variable. So you've seen independent variables and dependent variables earlier in this class, probably earlier in your life. But the new thing here is this intermediate variables. So X and Y are inherently functions of S and T, but they're the inputs for Z. Okay, so let's just talk briefly about higher dimensions, just kind of how we were formulating just previously, but I kind of want to put it into text. So in higher dimensions, the same kind of logic applies. So suppose I have a function w that is of x, y, and z. We have x is a function of s and t. We have that y is a function of s and t. And we also have that z is a function of s and t. So if I wanted to find partial w, partial s, very similar to how we did with two variables. So we're doing three groupings because there's three coordinates. There's x, y, and z. So we did partial y, partial s. And then we'll have this third term here, partial w, partial z, partial s. And of course, we also have to talk about when we take a partial with respect to t. So we have partial w, partial x, partial t, plus partial w, partial y, partial t, and partial w, partial z, partial t. And you can extend this to even higher and higher dimensions, right? So there's three groupings here because there's three intermediate variables and so on. So if we have 4 or 5, we would keep on tacking on those terms. Now notice if these depend on more variables, maybe we have S, T, and a third one, that doesn't change how many groupings there are. It just makes it so that we'll have 3 expressions here. So if there was a third, you would have to put in another one here. But luckily, we only depend on 2. Okay, so let's do an example. So we're going to express partial w, partial s, and partial w, partial t in terms of s and t when we have that w is equal to x plus 2y plus z squared. We have that x is s over t. We have that y is equal to s squared plus the natural log of t. And then z is 2s. Okay, so let's start with partial w, partial s. We know the form that this needs to take. So I'll quickly scribble that down. And now let's look at each one of these individually. So partial w, partial x. If I take an x derivative here, I only get a 1. And then I have to look at partial x, partial s. So I'm taking an s derivative here. This just gives me a 1 over t. Then I take a y derivative of w, so I get a 2, followed by partial y, partial s. This just gives me a 2s. And then I have partial w, partial z. This will give me a 2z. And then I have to do a partial z, partial s, and this will just give me a 2. So this is 1 over t plus 4s plus, so what I'll do is I'll substitute in z, because I need this in terms of s and t. So I substitute in z is equal to 2s. So this term here is 4s, or multiplied by this 2, we get an 8s. We can simplify that. It's just 1 over t plus 12s. See, that is an example of when plugging in all of these expressions into x, y, and z, make this very, very drawn out, right? Whereas we can take derivatives fairly quickly of each individual term and then use the chain rule to quickly get the answer. So all those partials are pretty easy. So now let's do a partial w, partial t. So let's quickly scribble down the definition. This also gives us practice of trying to see if we can do this offhand. Okay, so now we need partial w, partial x. Again, this is just going to be a 1. Then we have partial x, partial t. In this case, we have negative s over t squared. Then again, for partial w, partial y, I get a 2. But this time I have partial y, partial t. This just gives me a 1 over t. And then I have a partial w, partial z, which again will be a 2z. But this time I have a partial z, partial t, but there is no t expression in the z. So I just get a 0 here. This gives me a negative s over t squared plus a 2 over t, which I can simplify just a little bit and write as 2t minus s over t squared. Again, that was pretty easy, right? All these partials weren't too bad. And in fact, the first whole groupings were exactly the same. Notice that we have partial w, partial x, and partial w, partial y, partial z, or partial w, partial z on each of those terms. So once I've calculated them for the first time, it's really easy to just kind of write them down again and again and again for any other partial derivative that we're taking. Okay, so sometimes it's really helpful to draw what we're going to call tree diagrams. So a tree diagram just kind of visually displays how each of these variables are related to one another. So imagine that we had a function, we had a z, and it was reliant on two variables, x and y. So we can draw it something like this. But then x and y are inherently also functions of s and t. So I can read this off. I say, oh, okay, there's two variables, x and y. So I know I should have two groupings of terms for my chain rule. And I should also have, because these inherently are split into two, I should have a partial s and a partial t definition. I could also do something that we've kind of just done above, where maybe I have a w, and it's reliant on an x, y, and a z. But each of these inherently is a function of s and t. So I know I should have three groupings in my chain rule, and I should have a partial s and a partial t definition for my chain rules. And you can kind of extend that even further, right? Maybe it has four intermediate variables, or maybe it has three dependent variables. But this chain or this like kind of tree kind of helps us visualize what's going on, right? If that helps you, here it is. If it doesn't, yeah, okay. You don't have to use it. Okay. So today we're also going to continue with implicit differentiation. So when we learned about partial derivatives, there was nothing stopping us from using implicit differentiation when we did it from Calc 1, but this takes it a step further. So we could have used implicit differentiation for partial derivatives, but now we're going to talk about it beyond our comprehension from Calc 1. More specifically, we're going to talk about why we can do it, right? If you learned in Calc 1 this implicit differentiation, there was no one said this is the way why this works, right? We needed Calc 3 for that. So the chain rule can be used to further explain implicit differentiation. From Calc 1. So consider a function that we'll call capital F, and it relies on x and y. But we also have that y is inherently a function of one variable and it relies on x. We find this function f of x such that when we plug it in to our function of two variables, we end up with 0. So we're given this capital F function, and our goal is we define y to be a function of just x, so that when we plug it in to this capital F function, it ends up giving us 0. So capital F is inherently a function of only one variable at this point, right? Because we've subbed it in. But there's this intermediate variable y. So if we apply a d dx to each side, so we're looking at d dx of f of x and y, and a d dx of 0, which you can imagine just gives us a 0. We have to use the chain rule on this because y is inherently a function of x. So we have a partial capital F, partial x, dx dx, plus a partial f, partial y, dy dx, and this is still equal to 0. Now, of course, this dx dx is just 1, so that's pretty nice. But if partial f, partial y does not equal 0, then what we can do is solve for dy dx as negative partial capital F, partial x, over partial capital F, partial y. Or we can just kind of write that a little bit more compactly. Why are you doing partials here when you apply d dx? Because we have to do the chain rule. This is the case 1. This is case 1 for the chain rule for a function of more than one variable. So our family tree looks like x and y, where y is a function of x. Yeah, so we're doing the case 1 here. And you could put x is a function of x, right? And that's why you get this little guy right here, but this is just 1. Okay, so this is known as the implicit function theorem. Okay, so it might not look like anything right now, right? It might just look like, what is he doing here? I don't understand what's going on. I think it's best to kind of see an example. So we're going to find dy dx when we have that x squared plus sine of y minus 2y is equal to 0. And we're going to do it the Calc 1 way first, and then we're going to see how much easier it is doing the Calc 3 way. So back in Calc 1, what we did was we applied d dx to both sides. So we have an x squared plus sine of y minus 2y is equal to d dx of 0. So we'll just get 0 on that right-hand side. But this left-hand side, this becomes 2x dx, and that will just be 1. And then we have cosine y, but we have to take the derivative of the inside, which will give us 2y dx. And then we'll have minus 2 dy dx. And this is equal to 0. So our dx is just 1. So we can solve for dy dx here. So we have a 2x, and then I can factor out a dy dx here, and this will be a cosine of y minus 2 is equal to 0. So we can write that dy dx is equal to, we move this term over, so we get a minus 2x, and then we divide by a cosine of y minus 2. Okay, so wasn't so bad, right? These functions are actually pretty nice, but this is how we would do it the Calc 1 way, using implicit differentiation. Well, the Calc 3 way, so remember, our capital function needed to be equal to 0. And you can always rearrange algebraically to make sure that you get 0 on one of the sides. So we have an x squared plus a sine of y minus 2y is equal to 0. So this just means that our capital F function is equal to this left-hand side here, that thing that's equal to 0, plus sine of y minus 2y. And all we do is just take these partial derivatives. I look at partial x, so I go through and take the partial x derivative. This just gives me 2x. And I look at partial y. This just gives me a cosine of y minus 2. And then from our implicit function theorem, I knew that dy dx was equal to negative fx over fy, which is just negative 2x over cosine y minus 2. Same thing. And this is a lot easier. All I did was this is equal to 0. I assigned this to be my f. I just take my partial derivatives real quick, and then I just plug it into the implicit function theorem, and then you're done. That's actually what's happening when you're doing, when you learned about implicit differentiation in Calc 1. Pretty cool. So I think it's a lot easier than doing it the Calc 1 way. Okay. So let's continue this for even higher dimensions. So in higher dimensions, we still need to find a function that's equal to 0. So the whole goal is we go up one dimension. Just like before, we had a capital F of x and y. Now, if we go up one more dimension, we have an x, y, and z. So z, we're just trying to find a lowercase function of x and y such that this is equal to 0. So when I do the chain rule through this, I can find that partial f, partial x, partial x, partial x. So I'm doing an x derivative through here, plus partial y, or sorry, partial capital F, partial y, partial y, partial x, plus partial f, partial z, partial z, partial x is equal to 0. And I also can do a partial y through this. So a partial f, partial x, partial x, partial y, plus a partial f, partial y, partial y, partial y, plus a partial f, partial z, and partial z, partial y. This is also equal to 0. So we can solve for these partial z, partial x, and partial z, partial y. So partial z, partial x is equal to negative partial f, partial x, partial f, partial z, which is equal to just a compact form, r fx over fc. Or we can also look at partial z, partial y, which is negative partial f, partial y, partial f, partial z, or negative fy over fz. So maybe you have a function, or you have an expression of x, y, and z is equal to 0, or something else that you can always algebraically make 0. You can find the implicit differentiation for partial z, partial x this way, rather than kind of trying to do it the Calc 1 way. I think there is a WebAssign question where you can do it the good old-fashioned Calc 1 way. You can do that implicit differentiation with partial derivatives through. But you could also do it using this implicit function theorem. So let's do an example where we do it this way. So find partial z, partial x, and partial z, partial y when z cubed minus xy plus yz is equal to negative y cubed plus 2. Why does our function have to be 0 to do this? It's because we want this 0 on this right-hand side. Because then when we do a differential operator on it, we don't have to worry about it getting out of hand. So we always maintain the 0 here, so it's very easy for us to solve. We'll also talk about level surfaces way down the line, and you can think of it like that once we get there. But in this case, we're just trying to make sure that that right-hand side remains 0. Otherwise, solving for these quantities would be a lot more difficult. So notice here that we don't have 0 on one of those sides, but we can algebraically manipulate this. So I can say that f of x, y, and z is equal to z cubed minus xy plus yz. And if I needed 0 on, say, this side, I can move these over. So I can have a plus y cubed minus 2. So that will be my capital F. So I can go ahead and quickly look at each of these partial derivatives. So fx, if I go through, I have only this one x here, so this gives me a negative y. I have an fy, which will be a negative x plus z plus 3y squared. And then for fz, I go through, I have a term here, which will give me a 3z squared. And then I have a z here, which will give me plus y. So after finding those three, all I need to do is just kind of plug them in. So I know that partial z, partial x is equal to negative fx over fc, which in this case is y over 3z squared plus y, and partial z, partial y, which is negative fx f. Oh, sorry, that should be a y on top. This is going to be our x minus z minus 3y squared over 3z squared plus y. So we could have done this similar to the Calc 1 way, where we looked at the expression here and we did an x derivative through it, and we know that z is a function of x and y. So we would get a dz dx from differentiating this term. We would also get a dz dx from differentiating this term. But then we would have to algebraically try to solve for these things. But we can use the implicit function theorem to kind of quickly go through that. So it is just an alternative to doing it the Calc 1 way. And with that, we are done with 11.5. So actually, that's perfect timing. Why don't we take our 5-minute break here, go get some water, go use the restroom, and we'll kind of resume. And we'll start with 11.6 in about 5 minutes. So we're looking at 11.6 now. So let's start this on a new page. So 11.6 is directional derivatives and the gradient vector. Okay. So we've kind of discussed the rate of change of some function f of x and y in the x and the y direction, right? So these are the slopes of the tangent lines along those corresponding traces. But we also kind of hinted at the fact that, what if we wanted to know the change of the function in an arbitrary direction, right? Can we express this in terms of things that we know? So if I wanted to have a direction in some arbitrary direction, so we're going to try to consider the rate of change along some arbitrary direction that we'll call u. And this time u is going to be this unit vector, but it points in some direction that we're interested in knowing the rate of change of. And this is in the xy plane. So let's kind of sketch out what's happening here. I have the x-axis and I have the y-axis. And maybe z is coming out of the screen, but we are interested in this point here. And we want to know the rate of change of the function in some arbitrary direction. Now, this is our u vector. And because it is a unit vector, what we could do is we have an x direction and a y direction, and we have some angle here, theta, and this is the point x naught, y naught. Well, the x component of this vector is simply cosine of theta because it's a unit vector. And up here we have sine of theta. So now what we're doing is we're going to imagine we travel from the point x naught, y naught to xy in the direction of the u vector by some multiple that we'll call h. So we're traveling h units in the u direction, since it's a unit vector. So we're just going h units in the u direction from the point x naught, y naught, and we're arriving at the point xy. So mathematically, that kind of just looks like I have at the point where the vector, or the point described by the vector xy is equal to our starting spot, x naught, y naught, and then I go h units in the u direction, which we said was AB. So we can write that as x naught plus AH and y naught plus BH. So the change in z, which is our function of x and y, is then, I can write this as delta z is equal to z minus z naught, or f at this new x location, which we said was x naught plus AH and y naught plus BH minus f of x naught and y naught. So you might see where we're kind of going with this. We're kind of setting up this limit definition here. Therefore, if I have the change in z over how far I go, I can write this as 1 over h my function at my new x location and new y location minus f at the old location but as we let h go to 0, we're moving a infinitesimally small amount in the u direction, right? And this is setting up the limit definition for moving in the unit direction, or no, sorry, in the unit vector's direction. So the directional derivative the directional derivative of our function f at the point x naught, y naught in the direction of the unit vector u, which is AB, is then, and we denote the directional derivative by a capital D, a subscript in the direction that it's going, and then f of x naught, y naught, so because we're calculating at the specific location, is the limit as h goes to 0, 1 over h, f x naught plus ah, y naught plus b times h, minus f at x naught, y naught. If the limit exists. So remember before, one of the notations for the partial derivatives was a capital D and then either an X or a Y. That just means you're doing a directional derivative in the X direction or the Y direction. this simply says I'm doing it in some arbitrary direction, as long as I kind of detail that with a unit vector. So we don't really want to calculate this using a limit. We will do an example where we do use the limit, but it might be interesting to kind of figure out what this is in terms of things that we already know. Because as we've kind of seen up here, we haven't even utilized this fact at all, right? So perhaps we can use this to kind of rewrite this limit in terms of things that we already know how to calculate. So let's start from there. Let's try to figure out how we can rewrite this. So let's define a function. And we'll call this g of h, which is our function f at x naught plus a times h plus y naught plus b times h. So remember, our x naught and y naught are a constant here, and our a and b is also a constant. It's the direction that we're going in. So this is just a function of one variable. This is h if we kind of consider this x naught, a, and y naught b all constants. So what we can do is notice that the derivative of g at 0, meaning how g changes with respect to h, but we're kind of approaching 0, is the limit as h goes to 0 of g of h minus g at 0 over h. We can also write this as, by plugging in our definition for g, the limit as h goes to 0 of 1 over h, and then f at x naught plus ah y naught plus b times h minus g at 0, which would end up just giving us f at x naught and y naught. But this thing here, we just said, was the directional derivative in the u direction at x naught, y naught. Well, okay. So this g function and its derivative at 0 is very closely related to this directional derivative. So if we can calculate g prime at 0, maybe we can write this in terms of something we know. But what we can do is also implement the chain rule because g prime at h, so now we're just looking back at our g function here, right? This is a function of two variables where I've now, so we have an x and a y, but I've plugged in functions of one variable, which is just h. So this is the case 1 of our chain rule here. This is partial f, partial x, dx, dh, plus partial f, partial y, dy, dh. when our function g was just a function of two variables, where we had that each one of those was a function of one variable, which was just h. Right, so we can use the chain rule. We'll end up with this. So then we can say that the directional derivative in the u direction is f, well, of f at x naught, y naught. We know that this is equal from before to g prime at 0. So all we need to do, if this is g prime at h, all we need to do is just plug in 0 here. So if we plug in 0, this is partial f partial x. So we can just write that as fx, and it's at when h is equal to 0. So we plug in h is equal to 0, we just get x naught and y naught. And then dx dh, this is just a, plus we have partial f partial y evaluated when h is 0. So we just get partial y at x naught and y naught. And then we have dy dh, which will just be phi. So it looks like all we need is to take a partial x and a partial y derivative in order to find what the directional derivative is, right? It's partial x in the a direction, scaled by a, and then partial y scaled by b. But we also can kind of characterize what a and b are in terms of the angle if we want to, from our plot from up above. We knew that the x component of u was just cosine of theta. And then we knew that the y component of our u vector was just sine of theta. So this is two ways that we can write this. If we know the angle from the x direction, we can write it using cosines and sines. If we know it's the unit vector's actual description, in terms of if we have an x component and a y component, in terms of a and b, we can write it using this form. Okay, let's do an example. We're going to use both definitions, meaning either this or the limit definition. So let's actually do it using the limit definition at least once. You've seen it. And then we'll do it from then on, doing it the good old-fashioned way, using these partials. So using both definitions, we're going to find the directional derivative of x squared plus xy at the point 1, 2 when u is 1 over root 2, 1 over root 2. Okay, so before we start, we have to ask ourselves, is the direction that is provided a unit vector? We should always ask ourselves this first, because that's going to screw up everything we do if it's not. So we look at this vector, it's 1 over root 2 and 1 over root 2. You can double check real quick. That is, in fact, a unit vector. Perfect. Okay, so now we can move forward. Let's do it the limit definition way. And then we can do it using the partial derivatives. So we're going to let our function, our f, be x squared plus x times y. And our x naught is 1. And our y naught is 2. So we're going to plug those in later. But for now, we're using this limit definition. So du of f at the point 1, 2 is equal to the limit as h goes to 0 of 1 over h. And now I have to substitute in everything into my f function. So anytime I have an x, I have an x naught plus a times h. So there I have it squared. And then I have another x here. So this is x naught plus h times a. And every time I have a y, I have to plug in a y naught plus bh. And then I'm subtracting f at x naught and y naught. So that's x naught squared plus x naught y naught. Okay, so now let's kind of try to simplify this a little bit. This is the limit as h goes to 0 of 1 over h. So I'm going to have to FOIL some stuff out. So I get an x naught squared plus a 2 a times h x naught plus a squared h squared. I also have an x naught times a y naught plus an x naught times a bh. I have an AH times a y naught. And then I have a ABH squared. And then I have my minus x naught squared plus, oh, this should be a minus, sorry, because we're subtracting that whole quantity. So that should be a minus right there. It should also be a minus. Minus x naught y naught. Okay, so after we're done foiling, let's kind of simplify a little bit further. So this is the limit as h goes to 0 of 1 over h. And let's kind of simplify with some of these square brackets. I have x naught squareds that end up canceling. So, and I have a bunch of other terms that are canceling. Notice I have this x naught y naught and x naught y naught here. And then the things that we're left with is a 2a h x naught plus a squared h squared plus an x naught times a bh plus a y naught times an ah plus an abh squared. So now what I can do is this 1 over h, I can pull it through. And notice that kind of reduces the powers of h's on a lot of these terms. So this is the limit as h goes to 0. This is just a 2a x naught. Then I have an a squared h. Then I have a x naught times a b. Then I have a y naught times an a. And here I have an a, b times an h. So h going to 0 here is really easy to calculate. All of the terms that have h's still just go to 0. So this is equal to 2a x naught plus x naught times b plus y naught times a. And now we can actually plug in the values for these things. This is 2 times our a was 1 over root 2, and x naught was 1. And then our x naught again was 1. Our b was 1 over root 2. And then for our y naught, we had 2. And then a was 1 over root 2. So we can plug all that in, and we end up with 5 over root 2. Okay, that was the limit way. I at least wanted you guys to at least see it once. It's very similar to doing the limit definition for functions of one variable after you plug everything in, right? Because everything is just still this limit of just h. I'm not talking about a limit in R2. Okay, so now let's use it. Let's do this using the partial derivatives. It's going to be way quicker. We need to calculate fx of our function, which is then just 2x plus y. We need to calculate fy, which in this case is just x. We need to calculate our derivatives at that point, 1, 2. We plug in 1, 2 into our x derivative, we get 4. We plug 1, 2 into our y derivative, and we end up with just 1. So our directional derivative of the function f at the point 1, 2 is equal to fx at 1, 2 times a plus fy at 1, 2 times b, which in this case is, this is 4 times 1 over root 2, or 4 over root 2, plus 1 times 1 over root 2, or 1 over root 2, or we get 5 over root 2. Hey, we got the same answer. Great. Let's never do the limit way again. So this is actually a really nice, simple form for a derivative in an arbitrary direction. As long as we have this unit vector, we can just simply write this in terms of our x and y derivatives, which is really, really nice. That is cool that it worked out so nicely there. Okay, so now we're going to talk about the gradient vector. So we're really starting to get into some of the material that's just going to keep showing up for the rest of the course. So now we're going to notice that our directional derivative in the u direction of our function f can be written in terms of our x and y partial derivatives, just scaled by a and b, where a and b come from our unit vector u. But what I see here is a term multiplied by a term and another term multiplied by a term added together. And you might kind of think about the dot product. So we're finally bringing back this dot product. So if we made a vector out of fx and fy, and we dotted it with the vector that's AB, this is u. This is the u vector. We can write the directional derivative as this dot product. So from here, this is the first time that we're going to define this. We define the gradient of the function x times y as this upside down delta here of f, x, and y. This is equal to the vector f, x, and f sub y. Just another way to write it, partial f, partial x times I hat plus partial f, partial y, j hat. So this is the first time we're going to see this operator here. It will not be the last. I believe we'll talk more about it later on. But for now, if it's just acting on a function f, this is what it does. It makes it into a vector where we take partial derivatives in each component. So you can imagine that if we had a function of more than two variables, we would extend this vector, but we would just have fx, fy, fz, and so on. So then we can write that the directional derivative in the u direction of our function f is the gradient of our function dotted with the direction that it's going. So now we can kind of think about what the dot product does, right? What's happening here and how does it relate to our directional derivative? Well, the dot product was used as our scalar projection, right? So this is the scalar projection of the gradient of our function onto the u vector. So way back when we learned about projections, we're finally bringing that back here. This is our scalar projection of our gradient vector that's produced by taking the gradient of f, and we're projecting that onto the u vector. How much of the gradient is in the u direction? That is our directional derivative. Okay, so let's do an example. Let's find the derivative of f of x and y, where our function is, let's actually move this down here so you have some room. X e to the y plus cosine of x times y. We're finding it at the point 2, 0 in the direction it's given by a, which is 3, -4. Okay, like I said last time, first thing that we should check, is the direction vector a unit vector? It's really easy to see that this is not a unit vector. So we have to turn it into one. We have to turn a into a unit vector. So first, we normalize a. So we'll say that u is a over the magnitude of a, which is 3, -4 over the square root of 3 squared plus -4 squared. This is 9 plus 16, which gives us a 25. And that just gives us a 5 in the denominator. So it looks like we have 3/5 and -4/5. Great. So now that we have our u vector, we can actually go ahead and calculate our directional derivative. So we need our x derivative here. So this is e to the y minus y times sine of x times y. And then f partial y is x e to the y minus x sine of x times y. So our gradient of f is equal to fx and fy, which in this case is e to the y minus y sine x times y, comma, x e to the y minus x sine of xy. So here's our first calculation of a gradient. So we need the gradient at the point 2, 1. So we're evaluating this, sorry, at 2, 0. So we go ahead and plug in. So we have e to 0 minus, we're going to have 0 times sine at 0. So this is just going to be 0. And then we have 2 times e to 0 minus 2 times sine of xy of 0. So this would just give us another 0. So this just gives us 1 and 2. So our directional derivative of f evaluated at 2, 0 is our gradient at that point, which we discovered was 1, 2. And we're dotting this with our u vector, which we found to be 3/5 and -4/5. So this gives us 3/5 minus 8/5, which is just -1. Cool. This is our first gradient calculation. We're gonna do a lot of those. Okay. How much more? Okay, we can keep going. We have about 8 minutes left. I think we can talk about just a brief topic here. The question is, so it's just another way to find a directional derivative, but with gradients. Yeah, they're actually the exact same, right? This is in fact, let me kind of scroll up. This is the same as writing this guy, right? So we can calculate the gradient and we can dot it with u. This is yeah, it's the same exact thing as saying, oh, I calculate fx, fy, and I multiply by a and b. Yeah, but we're going to use this gradient a lot, and it's really nice to think of this as this kind of graphical representation of we're projecting the gradient into the u direction. So we're definitely gonna get familiar with the gradient. Okay, so let's talk about functions. Of 3 variables. And of course, this can extend to more than 3 variables, but we'll just talk about 3 here. So the directional derivative can be redefined as the directional derivative in the u direction acting on some function. Instead of writing x, y, or z, I'm going to write it as this vector x naught that denotes the position that we're in. So you can write this now this is in the arbitrary dimension, in fact, if we kind of just generalize this. This is the limit as h goes to 0 of 1 over h. Our function x naught plus h in the u direction minus f at x naught. So very similar. So in case of the u vector might be in 3 dimensions, a, b, and c. So this would be x naught plus h times a and y naught plus h times b, and then z naught plus h times c, and so on. So you're just adding that extra coordinate there. The gradient so we still have the same notation, but now because we're in a higher dimension, we should have another vector element. So we'll have fx, fy, and we'll also have fc. This lets us write that the directional derivative in the u direction of our function of x, y, and z is equal to the gradient of f of x, y, and z, and we're dotting this with the u vector. So that's another really neat way of writing it as this dot product, is that it generalizes to even higher dimensions, right? It's always going to be the gradient dotted with the u vector, right? So we can use this like kind of vector notation of writing it to really simplify. Oh, it's not fx times a plus fy times b plus fz times c, and so on, depending on how many dimensions we're in. We can always write it as the gradient of f dotted with u, which is a really compact way of writing it. And the dot product still holds the property of projections in higher dimensions. So this still is the projection of the gradient onto the unit vector u. With that, why don't we call it a day? We'll start our weekend. We'll start with an example on Monday. And I think we're actually right on schedule too. So I think we're all caught up at this point. Maybe we're even a tad ahead. So we'll keep chugging along for our exam next week. Yeah, I know it's exam already coming up next week. I'll stick around for a few minutes until some of the TAs jump. Oh no, there's no TAs. There's no office hours today. I guess I'll just stick around for a few minutes if you guys have any questions or anything like that until the official end of lecture time. Otherwise, I will see you all on Monday. Have a good weekend. Please stay safe, and I'll see you guys then.